Hi everyone, I'm Brandon Laguerre and this is the Critical Design Review for Group D. Our project is the Distributed Sound Event Location System, also known as Diesel. In this group, we have Mark Judy and Drew King on the software team, and Brandon Laguerre and Kristen Tanda on the hardware team. We'll begin with the motivation for this project. For both humans and animals alike, the sounds we hear around us play a major part in allowing us to communicate and quickly make observations about the world around us. However, we're not always around to hear those sounds, so the main goal of this project was to use technology and different audio processing methods to convert the sounds that we aren't around to hear into useful information. This information can be used for many things, such as increasing safety and security, research, conservation of animals, and general hobby activities. We believe we can achieve this in a few major steps. First, a sound event will occur that will trigger an array of audio sensors. The data from the sound event will then be sent to our processing software to be identified. Once identified, our triangulation software will step in to determine the approximate location of the sound event. Finally, the ID and location of the sound will be displayed to the user on our web app. For the project specifications, we want the array of sensors to be connected to a central server that will run the audio processing software. The central server will analyze the sound from multiple sensors and will use filtering to determine whether the sounds are of the same origin. The sensors will also timestamp all audio that is transmitted to the central server. The central server will triangulate the location of the sound event using time of arrival. The central server is supported by a machine learning model trained from multiple categories of sounds for classification. The program will adjust for environmental factors such as temperature that may affect the distance of sound travel when determining the originating location of a sound event. Sensors will be mountable to pre-existing light or pole fixtures for outdoor applications or wall or ceiling mounts for indoor applications. Sensors will also be able to withstand various environmental outdoor conditions. For the project specifications, we want the array of sensors to be connected to a centralized server that will run the audio processing software. The central server will analyze the sound events from multiple sensors and will use filtering to determine whether the sounds are being analyzed are the same origin. The sensors will then timestamp all audio that is transmitted to the central server. The central server will triangulate the location of the sound event using time of arrival. The central server is supported by a machine learning model that is trained from multiple categories of sounds for classification. The program will adjust for environmental factors such as temperature that may affect the distance a sound might travel when determining the originating location of a sound event. For outdoor applications, the sensors can be mounted onto pre-existing light or utility pole fixtures, and for indoor applications, the sensors can be mounted to either a wall or ceiling. Sensors will also be able to withstand various environmental conditions for outdoor use. These are the project requirements. It must be able to identify the originating location of the sound event within 5 meters. It must be able to verify the sound is being analyzed from all sensors with greater than 90% accuracy. It must be able to identify what originated the sound event with greater than 80% accuracy. It must be able to analyze the location and label the sound event within 5 seconds. Have a minimum required distance between sensors of less than 5 meters and a maximum operating distance between sensors of greater than 100 meters. It must be able to determine the temperature of the environment within 1 degree Celsius. It must maintain a sensor weight of less than 5 pounds. It must have a sound event capture range of greater than 100 meters. It must be able to achieve an IP rating for the sensor greater than or better than I-45 IP. It must also maintain a cost of less than $500 US. This is the overall block diagram for the diesel system. The block diagram is split up into 4 central parts that are located at the center of the screen. These parts are the sensors, the wireless protocol, the central server, and the web interface. The sensor block is expanded upon above and includes the power supply, microphone, microcontroller, wireless module, and optional GPS module. The central server block is expanded upon down below and includes the sound detection processing, the sound classification algorithm, the time of arrival analysis, the multilateration algorithm, and the website hosting software. One of our first steps was to decide upon a microcontroller. These are the 4 main microcontrollers we were looking at. Initially, the MSP430 was our first thought due to prior experience with it in other classes. However, upon further consideration, we decided a more powerful processor could be more useful and may be able to assist in some of the simpler audio processing. So we decided to look at the Raspberry Pi, the BeagleBone, and the Teensy 4.0. We ended up choosing the Teensy 4.0 development board for use in prototyping our project. The Teensy has a very simple design and houses a powerful ARM Cortex M7 processor. The overall simplicity of the board and its compatibility with C, C++, and Arduino code made it an excellent choice for us. The ARM Cortex processor has the following specifications. Its operating voltage is between 3 to 3.3 volts. Its maximum clock frequency is 600 MHz. The number of I/O pins it has is 127. Its RAM size is 1 megabyte. The I/O pins have a digital voltage of either 1.8 volts or 3.3 volts. And the following connectivity it has is I2C, SPI, UART, USB OTG, CAN, and Ethernet. The diesel system will be powered by an array of rechargeable batteries. However, the microcontroller can only operate if it is being supplied with a voltage between 3 to 3.6 volts, and if the supply current is less than 110 milliamps. To make sure that the device is powered safely, a DC to DC converter was implemented before the VDD input.
For the batteries of the power supply, we went with the 18650 lithium-ion battery. It has a rated voltage of 3.7 volts, but can be charged up to 4.2 volts, and discharge all the way down to 2.5 volts. We mainly chose this battery because of its availability. It's used in flashlights, laptop batteries, and power tools. And in addition to its high voltage, it also has a low self-discharge rate, meaning it could be stored for long periods of time. For our application, we're using 2 batteries in series, giving us a total output of 7.4 volts. The power supply will also have a BMS, which stands for Battery Management System. One of the purposes of a BMS is to prevent overcharge. So as stated before, the lithium ion maximum voltage is 4.2 volts. So once the battery reaches a voltage of 4.2, the BMS will not let the battery charge beyond that point. The same thing with over discharge. Once the battery starts being discharged close to 2.5 volts, the BMS will cut power to the circuit. Last, the BMS will balance charge the battery cells to make sure that each battery cell is the same voltage. For our BMS, we will be using the TP4056. It's a lithium-ion charging IC, and it will charge the lithium-ion battery with constant current and constant voltage. For the solar panel, we compared monocrystalline, polycrystalline, and thin film solar panels. Based off of our research, we decided to go with polycrystalline because it maximizes price and efficiency. And for our application, thin film, the flexibility of thin film isn't necessary. The microphones are going to be used to detect the sound events. Because of this, we need to have high quality microphones, and this comes from a high sampling rate and bit resolution. With our research, we chose the Teensy Audio Shield because of its sampling rate and bit resolution, and it also interfaces easily with the Teensy. The microcontrollers will communicate to the central server using Wi-Fi. Because of this, we need a high data rate so they can communicate quickly. Based on our research, we chose the ESP32 Room because not only did it have a high data rate, it was also inexpensive, and it interfaces well with the Teensy. After a sound event has been detected, the camera will turn on and send a live video feed through the main application. This way the user will be able to identify and track the sound event. We decided to go with the OV2640 because it has a decent resolution and will interface well with the ESP32. As an optional addition, we would like to add a GPS module. This way the location of the sensor will be tracked, allowing it to be mobile. The main concern with implementing GPS is the power usage, which would cause more strain on the batteries. Based on our research, if we were to choose a GPS module, we would choose the Neo 6M, mainly because of its price and small size.
Hi, my name is Drew King. We will now discuss the software for our project. We will be using machine learning for our classification. Once the audio collected by the sensors has been determined to be of the same origin, we can then pre-process the collected audio through a Fourier transform. The result will be a visual representation of the spectrum of frequencies of the audio signal as it varies with time. This image can then be passed through a convolutional neural network to be classified. This displays a spectrogram of a dot wave file containing audio for the ESC50 dataset. This image represents 3 dimensions in a 2D graph. The x-axis displays time, the y-axis represents the frequency of the audio signal on a log scale, and the colors of the graph represent the amplitude of a given frequency at a given time, with the darker colors representing low amplitudes and the brighter colors representing high amplitudes. This resulting spectrogram produces an image representation of the audio signal. Since developing a CNN model is done through mostly a trial and error method, this process will be continuously done throughout the project. Code has been written to develop different models that can then be trained and compared. To compare these developed models, TensorBoard will be used. TensorBoard is a visualization toolkit that will provide tracking and graphical representations of the metrics such as loss and accuracy to easily compare the different models and find the one best suited for our needs. The data we'll use for training and testing purposes will be taken from multiple resources that provide the data freely. This will reduce the time of producing a working model since it will help eliminate the time-consuming task of data collection. To produce a CNN that is accurate and effective, training is necessary. This will be provided by the development of a separate program that will conduct this training. This developed program will use backpropagation to adjust weights of neurons based on the results of outputs in previous epochs during training. Testing will then be conducted where samples not given to the model during its training phase will be used for the model to classify the samples. The accuracy of the model's classifications of these testing samples will then be calculated to determine the model's accuracy. The CNN model and its neuron weights determined during training and testing can be saved with a .h5 file. This file can then be loaded by the central server whenever new data comes in to be classified without the need for retraining and testing. For our web application, we will use a mean stack. This is due to the use of JavaScript throughout the stack and the benefits provided by that continuity. As shown in the figure, the application will use AngularJS for the front end, Node.js with Express for our server and API, and MongoDB for our database. The following features will be required for a functioning user interface. The homepage will require a login and sign-up form. The dashboard will hold the data collected by the system. This will include a map that will show the user the location of the most recent sound event. The UI will also include a section to display the information for the most recent sound event that has been analyzed by our system, and a section to display the history of sound events collected by the system. The use case shows a simple view of a user's interaction with our web application. The user will first go to the web application's web address and will be presented with the options of either logging in if they are a returning user or signing up if they are a new one. If the user is new, they will complete the sign up process and then continue as if they were a returning user. The user will then be brought to a dashboard where they will have the ability to access the features discussed previously. The user can then continue to view the presented data or log out of the application.
Hi, I'm Mark, and I work mainly on programming the microcontroller and actually figuring out how to detect and locate sounds. Multilateration is a way to is a process to figure out the location of the sounds that are being emitted. It's based on time of arrival rather than angles, like in triangulation. A popular example of multilateration is GPS, but it involves complex math and the computations are quite intense. Um, the because the time of arrival is relative at each location, multilateration has a limited service area, and it can only accurately be determined uh, if the sound or object was emitted from within the perimeter of the base stations. In this case, the base stations are going to be the microcontroller units that we're using. The screenshot at the bottom shows signals being emitted from uh, like 3 cell towers for a cell phone to be able to figure out its location. But in this case, it's going to be the reverse. Some object is going to emit a sound, and then each station is going to detect or hear that sound at a certain time. There's an open source library written in C# and Rust, developed by the Navy. In order to make use of multilateration, we first have to detect if all the microcontrollers heard the same sound. One way to do this is with audio fingerprinting. A popular example of audio fingerprinting is Shazam, where you record sound and it tells you what song is currently being played. Instead of storing metadata along with each fingerprint, like the song title or artist, we're going to store time of arrival and the location that each fingerprint originated from. Because the surface area of our system isn't going to be too large, we're only going to need to maintain around 10 or 20 seconds of fingerprints for each sensor. The audio samples need to be short in order to maintain a precise time of arrival. We don't want to have a fingerprint associated with 10 seconds of sound, because then the time of arrival is going to be every 10 seconds, which won't help us figure out the location. It is possible to create fingerprints on the microcontroller unit because the processor on it has a lot of advanced audio processing hardware, but it would require some extra programming. Some open source libraries are available, including ChromaPrint. Programming the TNTs is essentially just like programming an Arduino, except it has custom libraries to support the hardware. Um, it supports C++, so 99% of C++ libraries should be able to run on the TNT. And the creator of TNT has actually created a lot of custom libraries, including an extensive audio processing library. The TNT is going to have to connect to the ESP32 for Wi-Fi and networking, the audio hardware, the GPS, and potentially a camera. The ESP32 may end up being used as a coprocessor because it has its own, it is its own microcontroller. Data from each microcontroller is going to need to be sent to a central server for processing. Each microcontroller should send its raw audio data as well as its current location and the time that the sound was recorded. The central server is going to have to run the multilateration algorithm as well as the fingerprinting algorithm and recognition system. It's going to need to communicate with the web server in order to make the locations of detected sounds available. And the fingerprint data could probably just be stored in memory and not use an actual database such as uh, MySQL. And it needs a static IP so that the microcontrollers can connect to it every time that they're turned on. Either a static IP or URL. Now on to the administrative content. We split up the work according to our respective expertises, and this chart is based off of the block diagram from earlier in the presentation. This is the project budget for the development microcontrollers, the development sensors. It may end up needing to be more because we might need more than 3 sensors. and some of the prices for things are different for the development boards that we're currently working on. We've paid for everything ourselves, and one thing that's neat about this project is that we can each work on a microcontroller because we need at least 3.
The graph shows our current progress. We have most of our research required for the project done. Our designing for both hardware and software are mostly complete, with only some minor tweaks needed to be completed. Our implementation and overall progress are on track to be completed on time. Some difficulties that we have come upon include, for the machine learning aspect of our project, acquiring the amount of data needed and the time-consuming nature of training a model. We have also had some difficulties of creating a robust system of audio fingerprinting due to having to use short audio samples to determine the audio data's time of arrival. There has been some difficulty in being able to accurately test the full capability of our microphones in respect to the distance that it will be able to pick up audio. With our MCU, we have discovered some libraries that could be useful, but lack any implementation in C++. Some plans that we have for a successful completion of the project is having weekly group chats and calls using Discord. We are also utilizing Trello to have a centralized organization location to view required tasks, tasks currently in progress by each group member, and tasks that have been completed.